Hello everyone. Today we discuss about detailed mathematical expression to find out the different parameters for a second order time domain response, like a maximum peak overshoot, rise time, steady state time. These parameters are derived from the mathematical equation. First of our today's study is time domain response. Just a minute. Time domain response of second order system. So this is our task today. Okay. So in the previous video we see that for a second order control system, the typical characteristics equation is given by, for a control block, say for example, if we consider here one input signal Rs and here one comparator, and this open loop transfer function which is equal to omega n squared divided by s into s plus 2 zeta omega n. This output, there is a feedback is present, is called unity feedback, that is 1, and this is output Cs. Now we know that the closed loop gain here Cs by Rs equals to omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared, where omega n equal to undamped natural frequency. Yes, right. Now consider our input signal, this Rs equal to unit step. So that's why this is 1 by s, because we already know that the Laplace transform of the unit step signal is known as 1 by s. Okay. So therefore we putting this value here. So therefore Cs equals to omega n square divided by s into s square plus 2 zeta omega ns plus omega n square. Okay. Now these are output expression in a Laplacian form, first of all. Okay. So now we see here one thing, that this term s square plus twice zeta omega ns plus omega n square. Okay. This term can be written by the expression this term can be represented by the expression this equals to s plus zeta omega n square plus omega n square 1 minus zeta square. Is it right or wrong? Because s square plus 2 zeta omega n s plus omega n square plus zeta square omega n square. So basically this part and this part are cancel out, so this is basically the same expression. Now one thing should be remembered, that this term is very important, this omega n square 1 minus zeta square. Basically this term is known as damped frequency omega d square. So here omega d equals to basically omega n root over 1 minus zeta square. So this is a damped frequency in our second order time domain response. So therefore we rewrite this output expression in another form. Say for example, this should be expressed by another expression. Say this is 1 by s minus the term is s square plus twice zeta omega n s plus omega n square. So here we write our expression s plus 2 zeta omega n. Okay, because if we LCM this term, then in the first part numerator the coming out s square plus 2 zeta omega n s plus omega n square, and here and minus s square 2 zeta omega n into s, so cancel out to each other. So only in the numerator the omega n squared is present. Okay, no other term is present. So we express this equation by this expression. Okay, so now we expressed 1 by s minus s plus 2 zeta omega n divided by s plus omega n zeta whole square plus omega d square. Okay, now we again write this equation by this is zeta omega n, one part is coming out here, and another part is that zeta omega n divided by s plus epsilon omega n whole square plus omega d whole square. So this is our output, Laplace transform of the output response. Okay, so now we already know that from the Laplacian characteristics that e to the power minus at into cos omega t, what is the Laplace transform? The Laplace transform is s plus a divided by s plus a whole square plus omega square. This is one theorem. And another is e to the power minus a, sorry, yes, right, at here. The Laplace transform of this function equals to omega divided by s plus a whole square plus omega square. This is omega. So these are cosine part, these are sine part, and basically the signal is look like a e to the power minus cos t is basically look like a, this is a damping, and the sine part is look like this. Okay, so now we rearrange this equation again. Now Cs is basically 1 by s minus s plus zeta omega n divided by s plus zeta omega n whole square omega d square. Okay, this is one part, and here we see that there is a no s plus, only omega n part is coming. So now, and here omega d. So rearrange this equation in this form. So now we can write that here zeta omega n, one omega d is present here, and another omega d is here, and the equation is s plus zeta omega n whole square plus omega d square. Okay, so this is another expression. Now if we take inverse Laplace, so now there is a ct, this is a 1, this is e to the power minus zeta omega n t, yes, right, cos omega dt minus, now this, what is the inverse Laplace? Zeta omega n by omega d, this is e to the power minus zeta omega n t, and this is sine omega dt. So this is our time independent response of the second order system first coming out here from here. So now here we see that omega n and omega d. So now we one thing, 1 minus e to the power minus zeta omega n t cos omega dt. Now if we put here omega d equal to omega n root over something, then therefore this is zeta root over zeta square to the power minus zeta omega n t into sine omega dt. So now this is our output response in a time domain for a second order system. Yes, right. Now from here some mathematical computation. If we common this term, from these two, then the another mathematical expression is given by this equation. Sorry, there is no e part is coming out. There is only, yes, right, only sine omega t, omega d to t. Okay. So now consider here one thing. This 1 minus zeta square root over is known as, let us consider this as sine phi and zeta equal to known as cos phi. Just for consideration. So now we can write 1 minus e to the power minus zeta omega n t divided by 1 minus zeta square. This is equal to sine phi into cos omega dt minus cos phi into sine omega dt. Okay. Now we can say that the next equation is ct equals to 1 minus e to the power minus zeta omega n t divided by 1 minus zeta square. Now this is the term coming out, sine theta cos phi cos theta sine phi. Now this is sine omega dt plus phi. This is an equation. Okay, right? Yes. Now from here sine phi cos phi. Now from here sine phi by cos phi, that is tan phi. What is the value of tan phi? Tan phi is equals to root over 1 minus zeta square by zeta. So what is the value of phi? Phi is basically tan inverse 1 minus zeta square by zeta. Okay, so this is our expression, and the error signal is given by, we already know that error signal et equal to basically rt minus ct. So basically the error signal is here rt equal to 1 because of the unit step function. So now what is the error signal in a time domain? So putting this value, we get this, the another expression e to the power minus this 1 minus zeta square sine omega dt plus phi. Putting the value here, omega t equals to omega n root over 1 minus omega zeta square, and phi equals to tan inverse root over 1 minus zeta square by zeta. Okay, so now this is an error signal represent. Okay, so now this is a fully derivation of the time domain response of second order control system first of all. So now we can calculate the different parameters in a control system. Say for example, first of all, our parameter is to calculate the rise time. Okay, now one thing should be remembered, that for a calculation of the rise time, okay, the rise time is the time. So first of all, our today in this lecture, our first calculation is rise time parameter. This is also expressed by TR. Okay, now we already know that the rise time is the time needed for the response to reach from 10% to 90% or 0 to 100% of the desired value of the output at the very instant, at the very first instant. So now when signal is going from 0% to 100% or 10% to 90% is known as the rise time of the system. So first of all, we derive from this expression. So what is our value of Ct in a second order system? Our Ct equals to 1 minus e to the power minus, yes, right, zeta omega n t divided by 1 minus zeta square into sine omega dt. That means sine omega n into 1 minus zeta square into t here. Okay, plus phi means tan inverse root over 1 minus zeta square by zeta. Okay, 1 minus zeta square by zeta. Okay, or we put here phi also, anyone. So now at the first instant when the time response reaches 100%, the desired value Ct equal to 1. That means when it is 1, because our step signal is 1. So when it is reached to this 1 value, that means it's equals to the output equals to the input, that is equal to the rise time. That is, this time is needed here. This time is needed is known as the rise time. 0 to 100% or 10% to 90%. Okay, anyone. So now this value equals to 1. So here putting CT equals to 1. So now here putting CT equals to 1. So that is our equation equals to e to the power minus. Again we write here e to the power minus zeta omega n t 1 minus zeta square sine omega n 1 minus zeta square into t plus pi. So this is another expression. So now here 1 cancel out t. So now we see that here only one part, that is sine in a bracket omega n root over 1 minus zeta square plus pi, that is equal to 0, and this time is also known as here now rise time. Okay, now the acceptable solution of this equation sine theta sine something equal to 0, that means equal to n pi. So only we consider here pi for the first value, that is therefore omega n 1 minus zeta square in a bracket tr plus pi, that is equals to pi. Okay, so now what is the value of tr? Tr is basically nothing but pi minus phi divided by omega n into 1 minus zeta square. So this is our expression of rise time. It goes from 10% to 90% value for this typical second order system. And one thing should be remembered, that if we talk about the transient response specification of a second order control system, basically this nature of this city, basically the nature of this city here, if we plot the time parameter and if we here plot our city, and this is our input signal, and this is the highest magnitude value equal to 1. Okay, so this is our input 1 and this is a 0. So the second order system is look like a, okay, and it will be equal to the input when it is goes to the settling time. So here this is known as steady state or settling time, and here is a time, this is known as the rise time, and where the amplitude of the output signal is goes to maximum, it is known as the peak time. Okay, and this is the known as maximum peak overshoot from this value from here to here. This is known as maximum peak overshoot, sorry. Okay, and this slope is basically depend on the damping factor zeta, that is this time is basically depend on this parameter zeta into omega n. Okay, and the output settling time is basically depend on the 2% value of the maximum signal. In the later part we will thoroughly discuss about this steady state time. Okay, now we discuss about our second parameter, which is also very important for the second order system behavior. To analyze the behavior of the second order system is known as maximum overshoot. Okay, this is denoted by MP. Okay, right? Yes, and also we calculate our next parameter, that is known as peak time, that is denoted by TP. Okay, so now what is a maximum overshoot? First of all, maximum overshoot is basically the output response at a peak time minus 1. That means at a peak time this output response minus 1. So now we get this value only. This is a maximum overshoot, CTP minus 1. So now what is the percentage of this MP? The percentage is CTP minus 1 divided by 1 into 100%. So this is a basically percentage expression. So now the time needed to reach the maximum overshoot is called the peak time and denoted by TP. It is observed that MP occurs when the slope of the time response curve after the initiation of the input signal is 0. Therefore the time response expression is differentiated and equated to 0. The peak time Tp can be determined by substituting the value of Tp in the time response expression, that is CTP, and MP can be determined. So now our expression is, we already know that Ct is equals to 1 minus e to the power minus zeta omega nt divided by 1 minus zeta square sine, in a bracket there is an omega 1 minus zeta square into t plus phi. These are expression. Okay, first of all, now we take derivative of this part, because for the peak time, for the maximum value determination, we can take derivative, that is maximum value equal to 0, that is dct by dt equals to 0. Therefore, if we take derivative of this equation, therefore we get e to the power minus zeta omega nt 1 minus zeta square omega n 1 minus zeta square, and here this term equal to cos omega n 1 minus zeta square. Okay, this is a t plus phi. This is a one part, and another part is minus omega n e to the power minus zeta omega nt divided by root over 1 minus zeta square sine omega n root over 1 minus zeta square to t plus phi. So this is another part. So now this value, that means dct by dt equals to getting 0. Now if this value equal to 0, therefore this right hand part equal to 0. So after some mathematical computation, we get the term, first of all, this value is getting omega n into 1 minus zeta square cos omega n 1 minus zeta square, okay, into t plus phi. Okay, this equals to zeta omega n sine omega n minus 1 by zeta square to t plus phi. Okay, so now from this expression, tan omega n into 1 minus zeta square into t plus phi, this is equals to 1 minus zeta square by zeta. Okay, so now from here you see that from here now phi, the putting the value of phi equal to tan inverse something. Now you already know that this is tan of omega n 1 minus zeta square t plus tan inverse 1 minus zeta square by zeta is equals to 1 minus zeta square by zeta. Okay, so from this equation we can write that, yes, that means this omega n into 1 minus zeta square is t is basically equal to n pi. Okay, for n equal to 0, 1, 2 respectively. Now from here the peak time is basically the instant occurring of the maximum overshoot when n equal to 1. First we putting n equal to 1, therefore peak time equals to pi divided by omega n minus root over 1 minus zeta square, that means pi by omega t basically. Okay, damped frequency. So now from here our one parameter is coming out, that is Tp, that is the peak time, also known as peak time. Okay, now at this peak time we can calculate our overshoot. Now what we can do, our next task is to determine the value of MP. Okay, first of all we can calculate the value of MP. So now what we can do, so first of all we know that CTP is basically 1 minus e to the power minus zeta omega nt root over 1 minus zeta square into sine omega n into 1 minus this into something plus phi. Okay, so now 1 minus e to the power minus zeta omega n, here we putting the value of Tp, that means pi divided by omega n 1 minus zeta square by 1 minus zeta square. Okay, now in the sine part, sine omega n 1 minus zeta square to t. Okay, next part is, and this t equals to basically tp. So basically put here the value pi divided by omega n divided by 1 minus zeta square plus pi. Okay, now if we breaking this two part, now again we can write here 1 minus e to the power minus zeta pi divided by 1 minus zeta square divided by 1 minus zeta square. This is basically nothing but sine. Yes, right, this is basically sine pi plus pi, because this part is cancelled out. Okay, so now what is the value of sine pi plus pi? That is equals to 1 minus e to the power minus zeta pi divided by 1 minus zeta square divided by 1 minus zeta square. This is basically minus of sine phi. That is very important. Now from here we already know that phi equals to tan inverse 1 minus zeta square by zeta. Okay, so now ct max ctb is basically 1 plus e to the power minus zeta pi 1 by 2 to the power 1 by this, and here this value is equals to 1 minus zeta square. So now this part is cancelled out. So now ctp is basically 1 plus e to the power minus zeta pi divided by 1 minus zeta square. So now what is the value of mp? Mp is basically output at peak time minus 1. So now if we compute this value, therefore mp is basically e to the power minus zeta pi divided by 1 minus zeta square. So now what is the percentage value? Now this is a percentage value. Now this is our final expression of peak overshoot e to the power zeta pi 1 minus zeta square. Okay. Okay, now we talk about our next parameter, settling time. That is known as the next parameter is settling time. The settling time, which is also known as TS, settling time. Okay, for an settling time calculation, just a minute. For a settling time for an underdamped system, the magnitude of the oscillation present in the output time response decay exponentially with the time constant parameter 1 by zeta omega n, and here the time needed to settle down oscillation within 2% of the desired value of the output is known as the settling time divided by TS, and basically this TS equal to 4 times of zeta omega n. This is a 2% value, and this is the approximately 4 times of the time constant of the system. And if we consider the 5%, for 5% this TS is basically 3 times. In the another video we will discuss about the general expression of the TS. If we put 3%, 4%, 5%, any percentage, then we get the appropriate value of the TS. Okay, so that's all for today.